that have been going on since he was with us last year. Gary, I will turn it over and thank you.
Okay, thanks, Janet. There's still an awful lot of background noise on my side, so I don't know if everyone has muted their phones. So I'm not sure. I'm just going to proceed, and hopefully, if you guys can all hear, we'll be good.
All right, someone has a really bad background. Try the *6.
Okay. I think we're okay. So, Janet, if you want to just come on and confirm that we can start, that would be helpful.
Yes, we're good to go. I just have Gary Parker with us from RSD, who is gracious enough to be with here our second time. He was referred to us by James and the guys at J&J, and he works with them. So I will turn it over to Gary for the Changing State of Refrigerant webinar. Thank you for being with us, Gary.
Okay. All right, Janet, thanks for the invite. Like I said, we went through this a year ago, and I call it the changing state of refrigerants because what we talked about a year ago is different than what we'll talk about today. It continues to evolve. Most of that is on a regulatory basis. So what I'm going to do is cover the regulations component first and kind of give you the background, and then we'll dig into product. Some of the regulations are...
Line 1. Craig Smith, line 1.
Some of the regulations are state-specific. I'm not going to cover all states, but you'll kind of get a flavor for what that's about. And there we go. If you're looking for follow-up information, if you go to our corporate site, which is rsd.net, we have what's called the Refrigerant Suite, and all the information that I'm going to cover is here under the Training tab. You can actually download a copy of this presentation. It's the one that's on there now is about 1 or 2 generations behind what we're talking about today, but usually they're updated periodically. Under the Literature and Technical tab, this is information on retrofit guides, PT charts, that sort of thing. The Regulatory tab talks about EPA rules and regs, talks about some state and local regs, mostly California at that point. The refrigerant digests here, those are single-page summaries that talk about a lot of the regulatory changes and kind of distills it down to a few bullet points, so it's a little easier to digest. So I'd suggest referring to those if you have a question. This slide just talks about our particular app, our RSD Notes app, and for the purpose of this conversation, on the left-hand side you'll see a PT chart. It's extremely important that you have one of these or your techs have one of these on their phone. There's way too much information available today to deal with it in a paper notebook or a fold-out PT chart. And as we get into this more, you'll understand why that information is important. So make sure your guys all have some version of this, whether it's Copeland's or Emerson's or Sporland. They've all got them. You just need to pick one. Acronyms that we'll talk about briefly. CARB is the California Air Resources Board. That's the governing body here in California. GWP is the global warming potential, and we'll refer to that. The GWP is based on CO2, which has a value of 1, and everything else are multiples of that. So like 404A has a GWP of 3,900, and the higher the number, the worse it is on the environmental or regulatory scale. Hydrocarbons was something we didn't talk about last year at all. We'll delve into those a little bit later. HCFCs are what we're phasing out today, primarily R22. Those are chlorine-containing refrigerants, and so that's significant because that's what was considered the ozone-depleting component. The current generation gases are HFCs, which are hydrofluorocarbons. Fast forward to today, this carbon component here, carbon atom, is what they classify as a high global warmer. And so that's a lot of focus on that today. HFOs are a new generation of refrigerants, no chlorine, no carbon. The main component there is a product called 1234YF, which is a pure refrigerant in a lot of applications, primarily automotive, but it's a building block or an ingredient in a lot of the new blends, and we'll touch on that. In California, we have what are called SLCPs, and there's a whole host of regulations tied to short-lived climate pollutants. And then finally, SNAP. SNAP is an EPA acronym that basically identifies products that are approved for use in new applications. And so circling back a few years, 134A had to be SNAP approved as an R12 replacement. And 407C had to be SNAP approved as a 22 replacement, and so on. So the piece here is either a product is either SNAP approved or they remove SNAP approval, and you'll hear that term, and that's what that refers to. So here in the U.S., all the way back in 1990, we started the phase out of ozone depleters. In 96, we banned CFCs, predominantly R12 and 502, so that was 23 years ago now. In 2010, new systems, new R22 systems, specifically air conditioning, were banned. In 2015, it got a little confusing. The EPA announced that they were going to remove SNAP approval from what they classified as high global warming refrigerants. And they gave us about a 6-month window to prepare for that. And so for about 2 years or so, we were moving in a direction where we were getting away from products like 404 and 507 in new systems. On the heels of that, there was an international amendment to the Montreal Protocol signed in 2016 that began the process of phasing down HFC refrigerants, and we'll touch on that in a minute here. Fast forward to 2017, the federal court, there was a lawsuit filed against the EPA that said that the decision that they made in 2015 was not valid or was not appropriate. And so the federal court came back and agreed with that suit, and they basically struck down the 2015 rule. And where this got confusing for everyone was for 2 years we were told we weren't allowed to use 404 in new systems. And then fast forward 2 years later, they kind of re-upped that. Now, most of the equipment manufacturers had already moved in another direction. They weren't going to go back and retool again. But for a mechanical contractor, this gets to be a point of concern from the customer standpoint because they're getting, in their mind, conflicting information. So just know that currently that rule, the 2015 rule, has been vacated. For technicians, in 2018 there was a new EPA 608 certification change. All your technicians have an EPA card. That's called a 608 card, and there's some new requirements that are tied to that, and we'll talk about that in a second. So real quick, this is one of the refrigerant digests we talked about, but this just summarizes what the international phase-down schedule is for HFCs. As you'll see, the U.S. has not signed on to this at this point. Every indication is that we will begin a phase-down here It's just a matter of what calendar and schedule that we're going to be on. So we are moving in a different direction. This summarizes the EPA SNAP rule that was vacated, and basically what they said was EPA SNAP Rule 20 was there to govern ozone depletion, and that although you could use it to control ozone depleting refrigerants, you couldn't use it to govern global warming. And so they did ban what you could use as a retrofit gas, but they did not prohibit manufacturers from continuing the use of products like 404 and 507 in new systems. And some of the slower movers, ice machine companies, people like that, continue to use 404. As far as technicians go, this is new information that I think a lot of people are not completely familiar with. Number one, any of your new technicians today are taking a different test than you would have taken as little as a year ago. And it basically includes new information that's relevant to current generation products and global warming and all of that. So that makes a lot of sense. Now, the other interesting part is for you guys as mechanicals, you're required to keep your technician's EPA certification on file for 3 years, even after they leave the company or leave the business. That is a change, and the logic behind it is, up until now, the property owner was the one that was required to keep records on all their refrigerant activity, but the EPA recognizes that it's the technicians that are really doing the work, so they want to know who the technician or contractor was that was involved in the service, and so they're going to want to keep records, and by extension, you need to keep all the data on your techs as well. Let's jump down here to the bottom for a second. This at the bottom, which took effect in January 1, talks about the allowable leak rate thresholds for various applications. And when the Clean Air Act was first established, systems over 50 pounds were regulated, and if you had a leak of over 35% of the system charge in a 12-month period, the system was in violation and action had to be taken. Well, as of this year, those leak rate thresholds have changed, and you'll see there's 3 different categories. For commercial refrigeration, systems over 500 pounds, the threshold is 20%. And you need to do leak inspections and have validation that that leak was fixed for 4 consecutive quarters before that system kind of goes off probation. On systems 50 to 500 pounds, the leak rate's down to 20% as well, but you just need to validate that once per year. We have more stringent requirements here in California in that regard, but that's what the EPA is asking for. Down in comfort conditioning, this is new. They've added systems 50 pounds and more for air conditioning, and the threshold is down to 10%. So if just doing the math, if a system's got a 50-pound charge, if you lose more than 5 pounds at any given time, that's technically in violation. Now, the reality is that you're probably not even getting a trouble call if the system's short 5 pounds of gas in that case. So most every system that you come across that's in this larger sizes is something that you really got to get your techs dialed in, that and your customers as well, that finding these leaks and getting them resolved completely is important. Now, how they're going to enforce all of this, I can't tell you that. I don't know. But you as contractors and technicians are now kind of in the field of play with respect to the record keeping. Now, circling back to this middle section up here where it says technicians and contractors, has to do with if you're retiring equipment, and it goes all the way down to systems with 5 pounds. You now need to keep records on even those small systems and keep track of the location, date, and refrigerant type that was in the system, the amount of refrigerant you recovered, and what you did with the refrigerant. In other words, it went to reclaim, or you gave it back to the customer for on-site use or what have you. So if you think about a 5-pound system charge and you're looking at air conditioning, anything down to about a 2-ton system is going to have 5 pounds in it. So most every system that you have today, you're going to need to keep records on what happened to the refrigerant. The one point I would make was that if you go to a job site and you do a system change out, having the scrap guy take the unit away and having him responsible for the refrigerant recovery doesn't absolve you of the responsibility. You're the 608 card holders. So it's important that you take ownership of evacuating those systems, whether you use a recovery company or not. I mean, that's up to you, but don't just assume that because you didn't dispose of the unit that you're not responsible for the gas. So in California, I won't spend a lot of time. I know there's a couple of companies out here that are involved, but we have what's called the Refrigerant Management Program, and it has very many of the same requirements that the EPA has now rolled out, but here we have to register systems, we have to do quarterly leak inspections or have continuous monitoring depending on the system, and then everything has to be registered. Just like you get registration on your car, you have to register your system with the state. We talked about SLCP regulations that started in California in 2015, and those are ongoing today. Here in California, it gets a little more interesting because at the end of last year, California wrote their own SNAP rules, and essentially they reestablished the SNAP rules that the federal court vacated back in 2017. So even though the EPA rule isn't enforced, California has a very similar rule about what refrigerants we can and cannot use. They have new proposed regulations that are coming out, and one of the most significant changes is that in 2023, they're going to want air conditioning equipment operating on refrigerants that are below 750 GWP. Right now, there isn't anything available in a non-flammable refrigerant that can meet this criteria. So there's a lot of work being done behind the scenes with chemical companies and equipment manufacturers to try to accommodate this requirement. At this point, we don't know if the date's actually going to hold, but this is the proposed date. So this is just a summary of what they call the California Cooling Act, and basically it's the exact same verbiage that was in the EPA SNAP Rule 20, and it just talks about applications and where particular refrigerants are banned, or what refrigerants are banned. The biggest one that we're dealing with here is where it says remote condensing units. Any built-up systems, walk-in coolers, restaurants, and so on, they can no longer use 404 and 507 in those systems effective January 1 of this year. Both of those are extremely popular gases. For those of you guys that are in refrigeration, you know that. And this is particularly in California, a lot of people are still not familiar that this rule is in place. Now, what are they proposing moving forward? We already talked about a ban on stationary air conditioning with a limit of 750 GWP. For stationary refrigeration, the new proposal, and this is primarily for supermarkets, but what they're saying is if an existing system would require more than 50 pounds of refrigerant, then that refrigerant would have to be below 150 GWP. Now, currently, the only products that meet that criteria are either CO2, which is R744, ammonia, or a few what we're going to call A2L or HFO refrigerants. These are mildly flammable. Hydrocarbons like propane or butane fall into this category, but the challenge is that they're basically wanting every supermarket in the state to be on a natural refrigerant, and there's a lot of uphill work that's got to happen before that's going to take place. The third section down here where it says sales restrictions is really gotten everyone's attention as well, and they're proposing in 2022 that they're going to ban every refrigerant that's above 1,500. We won't even have them on the shelf for service support. Now, they are carving out an exception for reclaimed refrigerant, and they're also carving out an exception for 410A. But with the way that it is now, virtually every refrigerant that we stock as a distributor would be taken off our shelf. Again, we don't know if this date's really going to happen. We don't know if they're going to change the GWP threshold. My discussions with the state, I've indicated that if they change that number to just 1,700 instead of 15, that it would at least open up the door for additional products like 407, which a lot of people are already using today, and that drawing the line at 15 is going to be, pretty aggressive, and there's going to be a lot of heartache. Just so that you know, there's 22 states that are now members of what they call the U.S. Climate Alliance, and in varying degrees, all of these states have committed to following a similar framework to what California is already proposing. So that was the reason I gave you that background. Is I don't know if your state's on this list, but basically all the blue states are following where California is. I guess you could, if you wanted to use the political term there. But it's all happening. They'll be rolling it out on different schedules simply because they can't announce it today and roll it out 2 years from now without all the legal checks and balances. Where does that leave us? There are some products that are starting to come on stream that may be viable solutions. This is a new product that Honeywell has developed called 466A. It is an HFO refrigerant blend, and does meet all the criteria for California. It's below the 750 threshold. It does look and feel like 410A, and it is non-flammable. That's unique in that the only other product capable of meeting that performance and GWP requirement is a product called R32. Now, we'll talk about R32 in a little bit, but R32 is a very high performing refrigerant. It's high pressure, but it's also classified as A2 flammable. So it's not as flammable as propane or butane, but at this point, our building code and fire code won't allow us to use a refrigerant above A1 non-flammable status, and the charge size would be limited to about 5 ounces. So very, very small systems at this point. Daikin is the big proponent of R32 right now, and they are producing equipment in Europe and Asia that operates on R32, and they are introducing it here on small window units, little PTAC units, small mini splits. So it is possible that your technicians could run into R32 systems today on very small applications. So there's a lot of work being done. One of the challenges with 466A is because it has a different chemical makeup, they've got to do a lot of work determining whether it's compatible with the existing materials of construction. In other words, they don't want it to be corrosive and find out a year later that they're having mechanical failures. That work's ongoing, and we'll probably hear about it. The slide says early 2019. Clearly, we haven't hit that, but this is the next generation of what we're looking at. In December, Carrier Corporation announced that their replacement for 410, low GWP replacement, would be a product called 454B. Now, the challenge with 454B is it's A2L flammable. And as I said before, unless they can get the building codes modified, they're going to be limited to this charge size on these systems. But as I said, there's a lot of work being done in the background, both on the regulatory side and on the chemical company and equipment OEM side to kind of get this going. I don't think that the OEMs are going to want to produce different equipment for different states. So once they find something that works, it's likely that that new platform will go nationwide. I would say with easily within the next 5 years. Where we're at now with 22, we're basically done production this year. Supply from the manufacturers is limited to about 4 million pounds. There's actually an abundance of 22 in the marketplace today just because people have it, stockpiled. You've noticed that the price is down probably close to half of what it was in 2017. That's not because they're making more, it's just because people are going to try to get rid of what they have left. So don't be deceived that the low price indicates that you're going to have product long term. The other minor change, if any of you work on low pressure centrifugals, R123 is also an HCFC, but it will be produced until 2030 because of the unique properties of those low pressure chillers. We estimate that the demand is about 20 million pounds this year, and where the shortfall is going to come from is either reclaimed product that's reintroduced into the market, retrofits, or equipment replacements. And we'll talk about retrofits here in a minute. So, Janet, I don't know if you want to ask for questions at this point, because I think there's a lot of information. I don't want to go too far down the path and have to go circle back for a question.
Go ahead. If anyone has questions, if you *6 to unmute, you can throw them out there for Gary. Or you can type them in the chat box.
Okay, I'll continue on and we can circle back, or if you want to just type in a question, I'll gather. Now that I see that we have that available, I'll respond to those. This is a little bit of a chemistry lesson, but I think it's important to understand what goes into these refrigerants, and you'll be able to make your own evaluation and kind of get a little bit better understanding. So this is a list of some commonly marketed refrigerants, primarily 22 replacements. 404A was used for over a decade in doing supermarkets, and you'll see it's a 3-component blend, 125, 134, 143. That's what that chart indicates, is the percentage of each ingredient that goes into the blend. And there's dozens. We started with 401A, and we're up to about 470 right now. Some of those R numbers have as many as 8 letters behind them. So there's probably 150 different refrigerant combinations that ASHRAE has sanctioned. By the way, ASHRAE doesn't look at these products and judge them based on their performance. They're strictly there to determine whether the product is safe for you to apply, and at that point they'll assign it a number. But those assignments don't indicate whether a product's good or bad. That's a different area. So if you look specifically at 407, you'll see I have 3 there, 407A, C, and F. There's actually 8 407s. They go up to G, or H now, I should say. What makes those all 407 is that they have the same 3 ingredients, 32, 125, and 134. And then the only thing that's different is the formulation of them. They're not all after the same application. Some are low temp, some are air conditioning. The letter simply means that 407A was the first one ASHRAE validated, and in this case, 407H was validated about a year ago. Now, one sidebar on this, of these components, R32 we talked about before, it's a high performance, mildly flammable element. In a refrigerant blend, you'll always notice that R32 and 125 are together. Or at least if there's R32, there's also 125. 125 is a flame retardant, and so R32 does all the work, and 125 keeps the R32 in a non-flammable condition. In fact, 410A is actually 50% R32 and 50% 125, so you kind of get the idea of how those work. Like 410A, R32 is a high pressure gas, so to come up with a product that would work in a similar to 22, they introduced a bunch of 134A into the blend, and that's your low pressure component. So R32 is the capacity, 125 is the flammability control, 134A is keeps the pressures where we want them. So that's basically how those products go together. It's a little more involved than that, but that's the idea. The other thing about HFC refrigerants, they are not compatible with mineral oils or natural oils, and so whenever we went to an HFC, we have to incorporate a synthetic oil. In our industry, we chose POE. And we'll talk about POE oil in a minute. 422, in my screen, the dialog box is covering this part of my screen. I don't know if that's the case for you, but what you'll see with 422 is it has 2 HFC ingredients, 125 and 134, and then it has a hydrocarbon, in this case R600 butane. The butane is there not for refrigeration performance, but to make the blend compatible or miscible with existing oils. What I will tell you is that these non-oil change refrigerants do come with a price to pay, and that oil return is only going to work in select applications, and you're going to give up capacity. And the reason for the capacity loss is because they have had to remove the R32 when they introduced the propane or the butane. So that just kind of keep that in mind. You might not have to change the oil, but you're going to give up some performance. One other thing that I wanted to point out was there are a lot of products out there with a lot of creative marketing behind them. And just because they have a glossy website and a lot of testimonials does not necessarily mean that these products are all they're cracked up to be. Now, I've highlighted a product here called 458A. It's also known as Blue On. They have a marketing machine that has no rival. And they've come in and said that they can replace 22, that they're equal performance, that they're low GWP, that they're low pressure, that they use less energy. that they're everything. I've highlighted two pieces to this and compared it to 407C. Number one, you're going to see that it has a lower percentage of R32. Not significantly so, but enough that it can't claim to have the same capacity. It's just not possible without those values. Also look at the 134A. It has a higher percentage of 134A. Well, that's justification for their claim that it does run at lower pressures. It also justifies that it's going to use less energy because the compressor's doing less work. So those two claims kind of are where they are. Oops, I'm sorry. Let me go back one. But just be in mind that Bluon's not a bad refrigerant, but they claim it's the best out there. 407C, by the way, was the best product when it was developed 30 years ago, and it's still the best. So just kind of keep that in mind. I fast-forwarded one slide here. Now I'll get into that. This is a comparison of 407C and 448A, which is an HFO refrigerant that we're using a lot now in supermarkets. And again, very simply, if you look at the percentages of the ingredients, 448A looks very much like 407, except they've taken out about 60% of the 134A and replaced it with 1234YF. Remember, 1234 is the replacement for 134A in cars. So by taking out 134, that's a high global warmer, replacing it with 1234, that's a low global warmer, they've given us a refrigerant with the same performance and a lower GWP. So that's kind of how that all works. And again, there's dozens and dozens of these new products out there. So when you're looking at a refrigerant, capacity or the performance is critical. And the application is also important. And so when you're comparing a product to, in this case, R22, you need to, number one, look at the operating conditions that are relevant to your system. So in this case, I'm looking at a low temperature application like a supermarket where we've got a minus 20 saturated suction and 105 degree condensing temperature, which would be a typical water-cooled supermarket application. Capacity in a low temp situation usually is very critical, so you want something that's going to be close, and to me anything that's below 90% performance is probably going to be a deal breaker. We used 404 for a long time to retrofit supermarkets. One of the challenges with 404 is it had what they call a higher mass flow. Mass flow has to do with the density of the refrigerant. If you could picture it this way, it's the molecules per square inch. And the higher the density, the more volume you have to pass through the expansion valve. So if you use an existing valve, the higher density means you're going to have higher pressure drop. Well, pressure drop is generally not a good thing in our systems. So to accommodate 404, we had to install a larger expansion valve. And we did that for a decade and sold hundreds of thousands of valves for supermarket retrofits. That continued on until about 10 years ago when 407A and 407F came on stream, and you could see that they have similar capacity and similar mass flow to 22. So in this case, you could get the performance you wanted with just a minor TXV adjustment. The other thing I remember we talked about was these pure HFCs require a synthetic oil, and so you'll see there it says lubricant required as POE. Down in the middle of the chart, you'll see some products that say POE, AB, or mineral. Those are your non-oil change refrigerants. And what you'll see there is that they have in common either low capacity or high mass flow or both. And so even though they market them as a quote-unquote drop-in, there is always something that you have to do. You might get away without changing the oil, but you're going to have to give up performance, and you may have to do some mechanical modifications to make the product effective in your system. Also, if you look at the GWP, 22 is at 1760. And there's not a lot of options on that list that are below that threshold, which again is a hot button. So when you take that all into consideration, in supermarkets today, 407A and 407F are the dominant options to replace 22. And there's still a lot of that going on. Costco, for example, is using all 407F. Kroger is using all 407A. 448A is that HFO refrigerant. Again, checks all the boxes, capacity, mass flow, and is a much, much lower GWP than the others. And in this case, the Safeway, Albertsons, Vons family of stores are all converting to 448A. And there's other products. There's 449A is another product that's in that arena, and I just gave you just a few examples here to kind of look at. Probably more in line with what you folks are involved in. In air conditioning, the same conditions exist, the same criteria needs to be looked at, but in this case, most air conditioning systems are air-cooled. So it's important that you look at capacity relative to the ambient temperature you're dealing with, which, you know, the ambient is directly related to the condensing temperature. So you'll see capacity at 85 ambient and or 105. And what you'll notice is that although some of these products do pretty well at 85, they start to struggle when you get into those higher ambients. And that's going to be true with any refrigerant. You're not changing anything with the mechanical side of the system. You're not improving the condensing the condenser size or anything like that. So you got to know that you're going to lose performance. Now, I included 407A and F on here strictly as an example of something you want to avoid. In an air conditioning application, both of those gases theoretically could deliver more capacity than 22. And on the surface, that seems like a good idea or a good opportunity, but what you have to understand is that this is capacity potential at the evaporator. And with 407F, if you absorb 14% more BTUs at the evaporator, you're really going to struggle with trying to reject that heat load at the condensing unit. So in this case, these items are shaded out simply because they have too much capacity and would cause you some long-term, system issues. So when you look at that with air conditioning, 407C is clearly your best option. Like I said before, it was the best solution almost 30 years ago when it was first developed, and it is still the best today. You just need to deal with POE oil. The non-oil change solutions down below, there's dozens of those. I'm just highlighting a few that are popular today. You'll notice all of those have a higher GWP than 22, and for those of you guys in California, it's very likely that we won't have these products available in as little as 5 years. I don't know what that date will be, but it's definitely moving in that direction. So we need to be aware when we're doing a retrofit, you know, what state we're going to leave our customer system in, performance-wise and or regulatory-wise. So that's a challenge. Lubricants is a pretty significant piece of this discussion. We talked about the need for synthetic oils with pure HFCs. But oil return is really what we're talking about. It's less about lubrication and more about making sure that the refrigerant and the oil are miscible, making sure that the oil is being returned to the crankcase. And the way that works is the oil molecules and the refrigerant molecules bond together, and the refrigerant's responsible for carrying the oil along. If you don't have that bond, then you're relying strictly on velocity and pressure to get the oil to move. If with these non-oil change solutions, you have to understand that the application window is limited. Performance-wise, we talked about the impact at high ambience, but also with respect to oil return, the system design is also going to have a lot to do with that. Is it close coupled? Is it a split system? You know, in a commercial sense, did they have properly sized suction risers and P-traps and all of that? With the non-miscible combinations, you end up with an event called oil logging that takes place. And not only is that bad for the compressor, but it also impacts system performance. And so basically, oil gets pumped out into the system because of pressure and temperature. It's going to clear the high side pretty easily, even with a non-miscible option. But on the low side, where you have low temperatures and low pressures, the oil is going to tend to get hung up in the evaporator. And if you can picture an evaporator coil and the bottom 2 or 3 rows of the coil are ended up where the oil hangs out, it effectively insulates the coil from the inside out. So you don't have the full heat transfer surface that was engineered into it. So if you can manage the oil return and keep the compressor satisfied, you're still not getting past the fact that you have oil logged in the evaporator and you're going to lose heat transfer. So that's a key. Years ago, when we first started doing this, the discussion was that that the oils themselves were not compatible, and that you had to do multiple oil changes to get a full percentage or a high percentage of POE in the system. Well, where we are today is it's widely agreed that the oils themselves are compatible. The only unknown is what percentage of POE you need to get good oil return. And that's going to vary based on the system. Packaged air conditioning, you probably get away with 10 to 20%. A split system or a medium temp refrigeration system, maybe you need 50% POE. In a low temp supermarket, you probably need 95 to 100%. So that's going to vary based on the system, based on the design, based on the temperatures, all of those things. And of course, each refrigerant has a different percentage of hydrocarbons. So just keep that in mind if you're going with these non-oil change solutions. There are also additives available. We've used oil additives for decades to help improve the lubrication properties of the oil. High discharge temperatures would break down mineral oil, and rather than changing the oil, we would simply just put an additive in there to kind of reinvigorate the lubrication properties. These new additives also give you the claim that they're improving system performance. And essentially what they're doing is improving oil return. and limiting the oil logging activity. And so by extension, getting more oil back to the crankcase improves the performance of the compressor. Getting more oil out of the evaporator improves the system performance. So it's not a mystery what they're doing. They're not changing the heat transfer properties of the refrigerant or changing the geometry of the compressor. They're simply just improving oil return. So POE oil had its challenges, and one of the reasons that we tried to avoid it early on was just like synthetic motor oils that keep your engine clean, synthetic refrigeration oils keep your refrigeration system clean. You put POE in a system, it's going to pick up any debris that's hanging out there. If you've had a burnout or high discharge temperatures, varnish or buildup on your valve plates is all going to be cleaned up, and generally it sticks it in a cap tube or an orifice somewhere, and it's something that you have to deal with. And so that's a real challenge. The other piece with POE is that it's very hygroscopic, in meaning it absorbs and retains moisture. Traditionally, we use a vacuum pump to address moisture in a system, but with POE oil, a vacuum pump will not generally pull you into a deep enough vacuum to deal with the moisture completely. So you have to make sure that you use a properly sized dryer and that has sufficient amount of desiccant to do the job. So you generally want to oversize your dryer when you're converting over to POE oil. Well, one of the myths about POE is that the solvent properties of the oil have a tendency to break down seals and O-rings in a system and cause leaks. And although it could theoretically expose a pinhole leak that was plugged with debris, the reality is that it is not really contributing to leaks. What's happening in a refrigeration system when you charge the system with refrigerant, the rubber seals, natural rubber seals and O-rings absorb the refrigerant and swell up. That's common, it's expected, and that's not an issue. When you remove the HCFC, keep in mind this is a chlorine refrigerant, and you pull the system down into vacuum, those O-rings are going to shrink to near their original size. Now, they may be fatigued at that point, but the takeaway is that when you recharge the system with an HFC minus the chlorine, it doesn't absorb as much. So the seal that swelled up and seated properly with 22 is not going to swell up to the same size when you replace the 22 with a product like 407C. So it's likely that O-ring or seal is going to leak after the retrofit. So it's very important that you make sure you account for that, both time and materials, to address all those seals and O-rings. And again, it's important to note that we're talking about rubber gaskets and O-rings. We're not talking about fiber gaskets. We're not talking about king valve gaskets or head gaskets or anything like that. This is just any kind of basically rubber O-ring designs. So where those are, Schrader cores and caps are on all systems. Of course, caps aren't always there, but we should have those for sure. Open drive shaft seals on larger compressors are also a thing. One thing you got to remember is you don't necessarily have to use a different seal material. You just need to use a new seal. Now, in a lot of cases, the manufacturers will have two different types of seals available, and they'll have an option for one that's resistant to the absorption event, and that's certainly not a wrong thing to do. It's just the main thing for you and your quoters and whatnot is just make sure that you account for changing all the seals. Now, Schrader's on a AC unit, you might have 2. On a supermarket, you might have 200. So it gets to be a much bigger challenge the more complex the system becomes. The other place that's really common where you'll see this is on solenoid-operated valves, EPRs, heat reclaim valves, or just straight on-off solenoids. Now, this is becoming less and less of a problem today simply because around the year 2000, all the valve manufacturers went to different seal designs. And so if it's a newer valve, they don't have O-rings in them anymore. Most supermarkets, in their scope of work on a retrofit, just tell the contractor to change all the valves rather than spend the money on a retrofit kit and the labor to rebuild the valve and hope that it worked. They just pay the money to have new valves put in. So if you're in that side of the business, that's certainly an area that you want to focus on. But the main takeaway is you just got to deal with these one way or the other. Excuse me just one second. Okay, so when we're talking about blended refrigerants, and these are all the 400 series refrigerants, by definition, these are multiple component refrigerants. We talked about 407 a little bit before. And they all have some measure of glide. And basically what that means is, in the case of 407C, when the refrigerant enters the evaporator, the R32 starts to boil off. Then the temperature rises a little bit. The 125 starts to boil off, then the temperature rises again, and then the 134A ultimately boils off. And the difference in temperature between when the first bubble evaporates and then the last drop evaporates is measured is called the glide. Refrigerants with glide have been misunderstood for a long time, and up until recently it hadn't been a big deal. 404, 410A, both have glide, but it's, in the case of 404, it's about 1.5 degrees. In the case of 410A, it's about 0.3 of a degree. And so you could treat them as a pure fluid without really any impact, but it's important to know how to really deal with these, what they call high glide refrigerants. So when you look at a PT chart, on the left you see 22, one pressure, one temperature. With a blended refrigerant, we have both a dew and a bubble value. And the difference between the dew and the bubble value is measured in temperature, and that's the glide. Now, the glide number itself doesn't mean anything. You don't have to use that for any calculation. It's just you need to be aware of refrigerants with glide and how to address the dew and bubble value. So the dew value is used to measure superheat. The bubble value is used to measure subcooling. And it's very important that you and your technicians are aware of how to use this information. So with superheat, we're going to use the dew value. Procedure is pretty straightforward, very similar to what we do now. You're going to use your gauges to determine the pressure at the coil outlet. You're going to use a thermometer to measure the temperature at that same point. Based on the pressure, you're going to record the dew temperature. And your superheat is the actual temperature that you measured minus the dew temperature. So in this example with 407C, we have 80 pounds on our gauge and a 60-degree surface temperature. 80 pounds yields a dew point of 50.7. And so our superheat is the 60 degrees we measured minus the 50.7, or in this case 9.3 degrees of superheat. Well, if you could get 9 degrees of superheat as a technician, you're going to be happy. That's going to be kind of a target. Now, just as an example, if we decide to use the bubble value by accident in that calculation, the formula is going to look a little bit more like this, and we're going to end up with a false superheat reading of about 20 degrees. The impact of that is, in most cases, if a guy sees 20 degrees of superheat, he's either going to open his TXV or add more gas in a critical charge system. And where he correctly had a system with 9 degrees of superheat, in this example, he is going to tune all that superheat out of the system and put the compressor at risk. So just by simply misreading the PT chart, you can really cause some problems. So very important. Now, today's world, a lot of your technicians use electronic manifolds. The good part about that is you put your gauges on, you clamp on your thermometer, and the gauge set will help you set your superheat or subcooling depending on what you're doing. And it solves a lot of that, the math problems and everything. The challenge that you have is if your technician has gauges that are 2 or 3 years old, chances are it doesn't have the newest generation refrigerants on it. So if he walks up to a system and it's operating on 407H, he doesn't have that in his toolbox. So he's going to either have to use some other refrigerant and hope that it's close, or you're going to need to upgrade the firmware on the gauges to account for that. The other thing that we run into, and I get this a lot when I do bigger groups, is I ask the techs if they use analog gauges, and a lot of them still do, which is fine, but they have to understand that those gauges go out of calibration. And so it's important that they keep those calibrated so that these types of calculations can be as accurate as possible. The other thing is thermometers are a big deal. I jokingly talk about guys that inherited an old Simpson thermometer from their uncle or their dad. Comes in an old leather case, and it's kind of vintage, and they like using it, which is great, except same situation, that you've got to make sure that it's calibrated and accurate. Otherwise, these types of calculations and adjustments aren't going to really be effective. So just like having the top quality hand tools, you need to have good quality instruments as well. By the way, we sell all that stuff, so if you're interested. Okay, subcooling, same kind of thing. I'm not going to spend a lot of time on this, but we're going to use the bubble point for that. We're going to use gauges to determine the pressure, thermometer to measure the temperature. Based on the pressure, we're going to capture the bubble value, and your subcooling is the actual temperature minus the bubble temperature. So in this example, with 407C, the temperature reading is 110, the pressure is 300. At 300, we have a bubble value of 120.4, and your subcooling is going to be the 120.4 minus the 110. So same scenario here. If you swap out those values, you're going to get a slightly different reading. Now, in the case of subcooling, it would give you higher subcooling, which is not necessarily a bad thing. It's just giving you a false positive, if you will. So you want to make sure that you account for that. Now, we talked about dew value for superheat and bubble value for subcooling, but when we're talking about characteristics of refrigerant within the evaporator, we look at R22. In the case of 22, we're going to enter the evaporator at 76 pounds at 45 degrees, and we're going to have a 45-degree coil all the way across. As long as we've got saturation or liquid and vapor in combination, that coil is going to remain 45 degrees. It's only when we get to that superheat phase right at the outlet of the coil where our temperatures are going to climb. And so we can size a coil based on 45-degree suction, And let's just say we want 60-degree supply air, we size our coil based on those conditions. With a blended refrigerant and evaporator, again, it's a different animal because of the glide. So in this case, at the evaporator at 80 pounds, our 407C is going to enter the evaporator at about 40 degrees. And so one of the misnomers about blended refrigerants is that because there's glide, you need more coil surface to do the same amount of work. Well, with 22, we had a 45-degree coil all the way across and a 15-degree TD. Well, with 407C, assuming you set your superheat correctly, we're going to have 40-degree liquid entering the evaporator. So instead of that 15-degree TD, we have a 20-degree split across the first few turns of our coil. So we get credit for that. At the outlet of the coil, right before we get to the superheat phase, we're going to be at the dew point, which is 50.7. So on the bottom third of your coil, you're going to give back all that credit that you gained up above. But the reality is the average temperature across the coil is still essentially the same as we had before, that 45 degrees. And so it's important when you're doing a coil selection or a control set point that you don't use the bubble, you don't use the dew, but you use the average. And this is a new concept, probably within the last 5 years or so, that the equipment manufacturers and control people have finally come around to understand this part. And so if you're setting an EPR or something along those lines, you want to use the average. Or if you're sizing a replacement coil, don't size it at 50 degrees and a 10-degree split. Size it based on the average. Same thing on the condenser coil. At this example, at 300 pounds, we've got vapor entering the evaporator at 128.4. We've got liquid leaving the evaporator minus any subcooling at around 120.4. But the average temperature across the whole coil is still about 125, which is essentially what we had with a typical 22 system. In this case, although the pressures are a little bit higher, the temperatures are the same, and it's important to understand the difference. People talk about blended refrigerants putting more work on the compressor. In this case, although the pressures are a little bit higher, it's the temperature really that you're concerned with, because temperature is what's going to kill the compressor. Although the pressures are higher, if you go back and you look at the difference between the suction and the discharge, the compression ratios are almost identical. And so that's the work. If you think about it in an automotive engine sense, it's what's your compression ratio? Do you have 3-to-1, 4-to-1, 6-to-1, whatever it is? Same thing on a refrigeration compressor. As long as the compression ratio is the same, all you're worried about is the discharge temperature. So you got to just keep that in mind. And like if you're doing a fan cycling control you're trying to maintain head pressure, if you cycle your fan based on the dew value, you're going to cycle your fan prematurely. If you cycle it based on the bubble value, you're going to run your fan a little longer than needed. If you cycle it based on the average, you're going to get very similar performance to what you had with 22. Kind of getting into the tail end of this here, and just to kind of wrap it up, these are some applications that we're working on with these new lower GWP refrigerants. Some of you may be dealing with low pressure centrifugals, R123. On the left-hand side of this table are the A1 non-flammables. On the right-hand side are our A2 mildly flammables. So there is a product called 1233ZD. It's one of those pure HFO molecules, and it is a replacement for 123 in new systems. It is not a retrofit gas. I don't know if you remember, 20 minutes ago we talked about that 123 is going to continue to be produced for another 10 years because of the complexities of centrifugal chillers and how they're not really retrofittable or effectively retrofitted. 134A for reach-in coolers and all of that. There's a couple of options there. In Europe and Asia, they're using mildly flammable refrigerants in those. 1234YF, we talked about that being a 134A replacement. And it has a GWP of below 1, but it is classified as A2L. So you won't see that in the U.S., at least at this point, until they change the codes. For 22, there's a variety of commercial application replacements. 448 tends to be the most common these days, but like I said, there are others like 449. Same with 404A. We didn't really think about having to retrofit 404 systems, but because there's a potential that the refrigerant may not be available long term, there is momentum now to start retrofitting 404 as well. For 410, up until a year ago, that left-hand box was empty, and we didn't have a replacement for 410 in a non-flammable sense. But 466A has kind of fit that bill. And then there's other products, again, that are going after that, like 454A that Chemours is developing. And there's others, but you can see that this is the applications and the regulatory piece is what is driving the chemical companies nuts because they don't know which regulation to settle on. The regs and rules are different in Europe and Asia than they are here. They're different in California than they are in Arizona. And so everybody's kind of making all these different options available, and then ultimately they'll have to figure out which ones finally survive. If you're doing supermarkets, I'm going to touch on this for about 2 minutes. We'd already talked about converting stores over to 407. In this case, we're talking about either a 0-degree evaporator for medium temp or a -20 evaporator for low temp. And what you'll see is comparing 22, 407F, and 448. The mass flows are very similar. The capacities are very good. And the GWP is in the favor of 448. So that's the momentum. We're involved in these all the time. We're doing probably 100 supermarket retrofits a year right now to 448A as a result of this information. For 404, systems that were already either built with 404 or systems that were already converted to from 22 to 404, the reverse is true here. That you'll notice that the mass flow on 448 is lower than 404. And so we'd either need to go in and adjust the expansion valve and close it off or replace the valve. Now, one thing that we don't necessarily think about is how the capacity on these systems changes. So 10 years ago, when you went to the supermarket to get your deli meat and your cheese, you could just walk up to the case and grab whatever you wanted. Today, what you have to do is open a glass door. So a lot of these cases had been retrofitted to incorporate glass doors. They also, at the same time, went in and put in LED lighting, which reduced the heat load even more on the case. And so when that case was originally engineered, it was an open case with incandescent lights and required, let's say if 10 feet a case required a 1-ton load. That same case with glass doors today is only a 10,000 BTU load. So the valve itself has already been closed about 25% to accommodate that design change. So in a case like that, you don't have enough lower or a downward adjustment in your valve. So we're having to go back and change expansion valves all over again to get to these low GWP refrigerants. Just a couple of things. Again, this is strictly supermarket stuff, but on these high discharge temperature refrigerants, they have to put some things on there to accommodate that. Liquid injection is Emerson's solution. It's an electronic module that monitors temperature and injects liquid refrigerant into the suction port of the compressor to keep the discharge temperatures in check. Sporlan has a little valve that they use for that as well. Effectively works like a TXV. You measure the discharge temperature at the outlet of the compressor, and then based on the valve setting, you're injecting liquid into the suction port. So those are called, this is kind of a mechanical solution to the liquid injection. Hydrocarbons. If you're working on any kind of commercial reach-ins, beverage cases, display cases, ice machines, propane and butane are part of our future. McDonald's, Starbucks, all their new undercounters are all hydrocarbons, and the importance here is this is more of a safety statement than anything else. This is pretty unique product. It's not like the propane and butane that we're used to dealing with. It is odorless gas, doesn't have odorant built into it. So it's essential that your technicians have a hydrocarbon leak detector when they're working on this type of system. The systems are labeled, but here again, one glass door reach-in looks very much like the next. The way that they're marking them is not only with labels, but they're also putting red sleeves on the process tubes. So that'll be another clue that you're dealing with a hydrocarbon. Super important that you leak check the system before you start putting tools on it. End users, most of them will ask you to take the units off-site to work on them. The design of the systems, a lot of times they'll build what they call a cassette, where the condenser, compressor, evaporator are all on a single little skid, and you basically just pull the cassette out and replace it with a new cassette, and then you take the old one off and repair it. So that's a different process than we've had in the past. To get around the charge size limits that we have, the 5.5 ounces, larger systems can have 2 standalone refrigerant circuits, meaning 2 compressors, 2 condensers, 2 evaporators. And you'll see that on your medium temp 2-door reach-ins. True's doing a lot of that right now, True equipment. Couple other things, the component parts are unique to hydrocarbons. Relays, contactors, overloads, thermostats, fan motors, defrost heaters, all of that stuff is specially designed to be safe to use with flammable refrigerants. You cannot substitute those parts. So if you're into that, you need to make sure your techs are aware. This is getting into heavy-duty supermarket stuff. CO2 is a big thing. Again, it's low GWP, but it is a way more complex system. I'm not going to get into it here. They're also getting involved in what they call compact ammonia. They're going with glycol, distributed loops. There's all sorts of different technologies that are coming on stream as a result of these refrigerant changes. And so depending on where your company is, these are all things that you're going to need to deal with. So at this point, there's really kind of a good stepping off point, and I could open up the floor for questions.
You see the one in the chat?
I don't. Where would I?
Oh, it says, do you know of any regulations of us or the customer needing to report it based on the amounts put in. It was from Chad.
I'm sorry, I didn't see I don't see the chat box on my screen, but there isn't any reporting requirements on the contractor. The reporting requirements are limited to the end user, and that's only on a state-by-state basis. The EPA doesn't require reporting. What they do require is recording of all the information, and the example would be as if you had a system that had 75 pounds in it, and on March 1st you replaced 10 pounds, and on March 20 or June 20th you replaced another 10 pounds. Well, you replaced 20 pounds in a system that holds 75. That system's now above the allowable leak rate threshold and technically in violation, and that's supposed to start a clock on getting it fixed. Well, the only way the regulators are going to find that is if they go in and look at the service records. And are they going to do that or not, I can't say. But it's incumbent upon you guys to make sure those records are available, and as well as your property owner needs to see that.
Perfect, thank you.
And there's another one from John Howell. What is out there for hydrocarbon leak testing?
Well, most of the major leak detector companies have specifically what's called a hydrocarbon leak detector. I don't have a model number in front of me to refer to, but we stock a couple of different models. I'm sure that your distributor, whoever that might be, is got availability of those. We use Infocon is the ones that we sell here, but there are others. But it is a unique leak detector to hydrocarbons.
Any other questions, anybody? All right. Well, thank you so much, Gary, for taking the time out to bring everybody up to speed. We really appreciate it. Look forward to working with you again in the future.
Well, I appreciate you inviting me in, and if there's, like I said, if you have questions, even if you're outside of our geography, you know, on the website there's an 800 number and an email address if you have questions. I'd be happy to field those for you guys. So, thanks again. Have a great holiday.
Thank you so much, and you too. And thanks, everybody, for being on the webinar. And we'll send a recording out after in the next couple days.